next presentation is unconfined non-premixed swirling frame, effect of swirl number on frame stabilization. Presenter is Dr. Saptarshi. I introduce the speaker. Dr. Basu is currently Associate Professor in the Department of Mechanical Engineering, Indian Institute of Science. Professor Basu leads large-scale initiatives in the area of combustion, voltage flow, and heat transfer. He is a project leader, National Center for Combustion Research and Development, and SERIIUS. Before joining IISC, Dr. Basu was an assistant professor in the Department of Mechanical and Material and Aerospace Engineering at the University of Central Florida from August 2007 to 2010. His current research interests include the combustion instability, frame vortex inversion, sprays, droplet combustion. Detailed introduction to this report or this abstract book.
Thank you. So the topic of this particular presentation is related to essentially swirling flows and flames. So this is basically the work that is done by my PhD student who has just graduated, R. Santosh. So what I am going to present over here is basically an overview of like the 4 papers that we brought out based on basically this work. So if you are interested in reading the papers, I can forward them to you at the end of the presentation because time is short for making a very long presentation in this context. So basically this is the overview. So we will first look at the background fluid mechanics of the problem and then move on to the flame. And there are some interesting transitions and primary and secondary that you see in the case of a coaxial swirling jet. So we will give an idea of what that is. So basically we all know that where is the need for lean combustion and what is the role of a swirling flow. So basically what you have over here is what is called a vortex breakdown bubble that is created in a swirling flow. Basically, it acts as a flame stabilization mechanism because it basically acts as a mixing zone in which the hot combustion products mixes with the incoming reactants. So basically, that is roughly the flow structure that you know. But fortunately or unfortunately, this particular flow structure is subject to a lot of research and nothing conclusive, like how this flow structure exactly forms, what is the dynamics of this particular structure is very hard to nail down. And one of the collateral damages of having lean combustion and having swirl is basically you have the typical picture in which you have a tightly coupled coupling between the heat release, acoustic oscillations, and the flow and mixture perturbations. So these 3 things actually combine in a loop, and it can lead to multiple instability mechanisms, principle of which is basically the thermoacoustic instability that you see. Okay, so there is a lot of literature that is based on this as well. On the hydrodynamic part of the swirling flows, okay, if you look at the picture on the left-hand side, left-hand corner, you find that there is as I already told you, that there is a vortex breakdown bubble, and you get basically 2 shear layers, prominent shear layers. One is called the inner shear layer, and one is called the outer shear layer. So the vortex breakdown bubble is basically an absolutely unstable structure. Thank you. So it's an absolutely unstable structure. So it shows patterns like a double helix type of a big breakdown or an axisymmetric breakdown or a cone breakdown. And we will see some of these things that how it actually happens. And of course, the shear layer instabilities are basically Kelvin-Helmholtz or convectively unstable in nature. And sometimes this vortex breakdown bubble would actually interact with the shear layer instabilities, and you get a lot of flow transitions. So we are going to principally look at some of these phenomena in a little bit more details. Some more on the vortex breakdown. It dates back quite a bit. There's a paper, landmark paper by Sarpakaya in JFM in 1971, where you essentially see there is an abrupt deceleration of the streamwise flow, and you get a stagnation point that is formed here, and you basically get this. This is an axisymmetric vortex breakdown structure. So this is quite common. This is what you see in the literature. Okay. So now let us look at this experimental setup. What we uniquely achieve over here, so this is the burner or the swirling flow. Both uses basically the same setup. What we have essentially is through an inner pipe, you can basically, it's a co-annular jet. So through the inner pipe, you have a jet. Through the annulus, you have another jet. And basically, the swirl is a radial swirler in nature. So basically, through these ports, you supply it with the required flow rate at whatever flow rate that you want. Basically, this allows us to have an independent control on the swirl number, okay, without basically resorting to guided vanes, because in that particular case, you have to continuously change the angle of the vane to get whatever the desired swirl number that you have. Okay, so and the measurement methodology uses a whole gamut of techniques, including high-speed PIV now, and CH and OH chemiluminescence, as well as pressure measurements and things like that. So this entire thing is what the setup actually looks like. Some of the important parameters over here, if you look at that, the principal parameters or the most important parameter that you can define over here, apart from the swirl number, is basically what we call the Rossby number effect. So the Rossby number is basically, if you see that delta Uy is basically a velocity deficit between the two streams. There are two streams, one coming from the central jet, one coming from the annulus. So there is a velocity deficit between the two. So essentially what it does is that it starts to create a toppling kind of a moment on the flow. So if we define the Rossby number essentially as that particular delta Uy divided by whatever is the tangential velocity that you are supplying. So the pressure drop that is associated with the rotational effects is basically given by the simple swirl number type of expression. The competing pressure gradient that arises, what we call due to the entrainment effect, will actually basically can be recasted in this particular form. You take the ratio of the two, it scales basically as Rossby number square. So essentially Rossby number much greater than 1 means the entrainment effect is dominant. Rossby number much less than 1 means essentially the swirl effect is very dominant. So you define what is called the swirl number. This definition, however, is, well, there are multiple definitions, but this is the most commonly accepted one. We also define the geometric swirl number. So this is also defined. So these two are linked by a factor k, which we will see later. So the sample space, if we show, is basically there are some time averaged velocities. These are the corresponding Reynolds number. This is the velocity ratio. This is the modified Rossby number. This is the swirl number. So if we look at the primary transitions, which I will show in the next slide, you find that the Rossby number varies from somewhere between larger than 1 to all the way up to 0. And we will see what the structure exactly looks like. The swirl number variation is not that much. It varies within a particular order. So what you see in the primary transition modes is that when you have the Rossby number about 3.5, you have a central jet and you have the two toroidal vortices on either side. So this is like a toroid like this, surrounds the central jet. As you go on to the Rossby number space of 1.12, what you have is that you have a basic deceleration of the jet. There is a reversal that you have of the flow over here. This particular zone becomes larger. As you go down and finally move to what we call the central toroidal recirculation zone, okay, you have the complete disappearance of the central jet. This is almost Rossby number equal to 0, roughly of the order of 0. So what we have in this particular slide, you can see, is that the effect of swirl number, though it has not changed by much, you get a complete transformation of the flow from an initial jet penetrated, which we call the pre-VB or the pre-vortex breakdown structure, to the complete CTRZ or the central toroidal recirculation zone. So that is the whole morphology that is seen over here. If you put them in the kind of a stability map, which is basically the swirl number plotted against the Rossby number, you find that I am traversing from here to here. This is where the CTRZ basically lies, and this is where the pre-vortex breakdown structure actually lies. There is no recirculation zone in this particular region. So if you also look at the distribution of the azimuthal velocity distribution, that is the u theta basically, and you plot it from the top view basically with r over r naught, what you find is that this blue lines indicate that how far the swirl influence is actually felt. And after that, you basically have the onset of solid body rotation. There is the profile looks almost like that. Okay, so the modified Rossby number, what it does is that it takes into account the net effect of rotational and the entrainment, essentially. We look at some of the, next what we did was that, so we found the primary transitions of the flow. Now, we decided after that, why not therefore now fix the Rossby number at 3 particular settings, high, medium, and low, and vary the swirl number, basically the geometric swirl number, over a very large distance, basically, essentially, from 2.14 to 3.97, 2.69 to 5, and 2.288 to somewhere around 5.39. And let us observe what kind of a changes does this actually show. And this shows a lot of interesting structures once again. So before I look at those structures, let us look at this. So here we define, once again, if you look at these particular plots, you will find that there is a Rossby number greater than 1, equal to 1, almost equal to 0 limits. And we define something called subcritical to supercritical transitions. So what happens is that this is the structure that you begin with, and you are increasing the swirl number. You are seeing this kind of a flow transitions. So basically, these are the flow transitions that happens in the case of pre-vortex breakdown bubble. You have the same type of transitions in the case of partially penetrated the vortex breakdown bubble, that is the intermediate stage. Here you see a spectacular breakdown structure. This is basically a conical breakdown of the vortex breakdown bubble, okay, with an increase in the geometric swirl number for a Rossby number value of around 1. And this structure, however, reverts back, okay, as you increase the geometric swirl number to the similar type. Morphologically, they are pretty close to each other, though they are very different if you look at the vorticity maps, okay. Same type of thing you get in the case of CTRZ, the central toroidal recirculation zone. You get a complete conical breakdown when you actually traverse in the swirl number axis. So this is what we call the secondary transitions. So if you put the same thing now on this stability map, what you find is that this is the critical stage where the fanning actually happens. So you're basically moving up like this. So from 3 is what we saw was the central toroidal recirculation zone. You move up, you move to the critical zone, and this 3 double prime that you see is basically you move to the supercritical stage, which is basically 4 and 3 in this particular figure. So every time we are traversing like this, okay, and these are the corresponding stages, so subcritical, critical, and supercritical. So these are the transitions that you see when you actually fix the Rossby number and just increase the swirl number effect. And just a brief also understanding that you get just by looking at basically the map of the velocity. So I will come across to this a little later. But how to understanding the secondary transition is not very well. This is a hypothesis. So you have essentially, as I mentioned earlier, you have a radial pressure gradient that is created due to the rotation. You have a pressure gradient that is created due to entrainment. They oppose each other. So as you increase the swirl, you have more penetration essentially of the swirl influence inside the burner cone, inside the burner central axis. However, when you are actually dealing with the conical type breakdown, you remember that the Rossby number is practically equal to 0. So this essentially means that the swirl actually penetrates and interacts with basically the vortex core center, and you basically pump in a lot of energy over here, leads to this catastrophic conical type breakdown of the whole structure. If you look at the same thing, we defined a parameter which is basically called the swirl momentum parameter. Now the swirl momentum parameter is interesting. It shows basically what is the effectiveness of the inward diffusion of the angular momentum from the co-annular jet towards the jet center axis. So essentially what you look at in this particular plot is that for the particular swirl number range, and particularly when the Rossby number is much less than 1, you get a band in which you have this particular activity. There is almost like a 3 times change in the, or an increase, basically translates to something like 100% increase in this swirl momentum parameter, indicating the narrow band in which the conical sheet breakdown actually happens. Okay. We look next in this particular fluid mechanics from these issues, we look at also the response characteristics. So basically the role of acoustics in the structure, that how these structures actually behave when you actually have acoustics. So what I'm going to show in this particular map is that we are going to take each of these structure and we are going to basically excite them and then look at how they actually behave. So how a subcritical structure behave to acoustics, how does a critical structure behave to acoustics, and how does a supercritical structure behaves to acoustics. And we will see that in the next one. And there were a number of amplitudes that we actually did, that basically these amplitudes are increasing increasing in magnitude. However, the frequency of excitation, though we tried a lot of a broadband range, but basically the response features lies within basically 100 to 120 hertz, basically in that window. So it basically is prudent to excite it at these particular values. A5 represents the highest amplitude, A1 represents the lowest amplitude in this scenario. Now, if we look at the subcritical CTRZ now, so CTRZ is an interesting structure. So basically because the Rossby number is almost equal to 0 over there. So it's almost like a swirling co-annular jet, but without any central flow. So it is almost like a bluff body. That thing acts almost like a bluff body over here. So what you have over here, if you look at the vortex interaction, you find that at certain amplitudes, absolutely no response really happens. But however, when you actually pump energy, say there is a certain critical threshold like C3, okay, which is some intermediate value, you once again do get this conical breakdown. It once again happens. Okay, so it happens at 100 hertz, and when you have sufficient excitation, it actually changes quite a bit. So here also we define a parameter called the aerodynamic blockage ratio, which is basically the blockage that happens due to the frequency response normalized by whatever was the blockage at 0 hertz. That means the no response case. That means there is no acoustics essentially. Similarly, when we look at the supercritical CTRZ over here, once again you see that supercritical CTRZ also shows a similar type of conical breakdown. Once again, that particular breakdown happens somewhere around the A5 threshold amplitude. The topology severely broadens. So we were able to put all of these things now in the stability map, where now each of these transitions, where you see that nice little acoustic horn, that actually represents what is the corresponding acoustically excited structure that you see. And the aerodynamic blockage ratio increases in those cases by quite a bit. Like there's from 1.55, it moves all the way up to 3. So these are the flow features that you get. To see the acoustic vortex interaction, the local response structures, what we did was that let's look at the subcritical CTRZ, which does not actually show that does not show any conical breakdown as such. What we find over here, what we did was that we traversed our anemometer right from 1 all the way up to 9 and measured basically the PSDs. Okay, so when the excitation was at 100 hertz, obviously the peak should show up, okay, in those particular regions. But however, once you go outside this region B essentially, okay, your peak basically vanishes. Okay, so that means your zone of influence essentially, okay, here this portion B that you see over here, beyond B you don't get any peak, but however within B you always get a peak over here, and this area, this B actually is a dynamic parameter. It broadens as you pump more and more acoustic energy into the flow. Okay. However, when you look at the supercritical CTRZ, which do undergo the conical breakdown, okay, Okay? As you traverse, the variation in B is minuscule. So beyond B, you do not get to see anything. So the acoustic energy is a lot more concentrated. That means you don't decipher any peak either side as you traverse out of B. There is no observable peaks, and this is clearly shown by the hot wire anemometry data. So as you move from here to here. So the acoustic energy is basically being pumped within a very small region. So this further proves the point that if you try to understand the difference between subcritical and supercritical CTRZ, or the vortex breakdown states, once again, because these states correspond to very weak Rossby number, so essentially what happens is that as you have the swirl number is about 2.88, so you have a comparatively weak swirl influence. As you pump acoustic energy, there is a pathway for the acoustic transport basically from the from near the vortex breakdown bubble to basically the OSLs. And so there is a clear evidence of ISL and IRZ interaction. So that's why you get a broadening of B that you see here. So B is basically designated as the path or the zone of influence. As you move on to the higher swirl number, which is 4, so you have a very strong rotational influence over here, and this is directed inwards essentially. So your acoustic energy basically feels a blockage. So there is no radial transport essentially. So there is a reduced ISL-IRZ interaction. Once again, you put more energy into a system, and it's a confined energy. It undergoes what we call the conical breakdown. So based on all these observations, okay, I have a little bit of a time. So we started to move into the corresponding non-premixed swirling flame dynamics. It's essentially the same burner. The fuel is fed through the inner pipe. The air and the swirl comes through the outer, so the annular portion and to the swirl vanes. Once again, it allows 3 levels of control. So that means you can control Rossby number and swirl number independently in this particular experiment. And we use basically PIV in the flame as well as OH, high-speed OH chemiluminescence imaging for doing the same. This is the corresponding case. So we take out a few cases and try to study what actually happens. So if you look at, once again, a similar stability diagram, this time, however, with swirl number versus the Reynolds number. Reynolds number is based on the annular flow rate. You get this kind of a plot in which B2 basically corresponds to no coannular flow. So basically, coannular flow in which there is a prominence, very high level of swirl. So you get called a pure swirl blowout kind of a scenario. You move to the other extreme of the spectrum in which there is no swirl, just a jet. So you basically get a blow off. So that means the flame is just lifts off and vanishes. In between, you get, this is basically the subcritical structure coming from the hydrodynamic point of view that we saw in the flow. And this is basically the supercritical structure. In between, you see in these, if you traverse just by just changing the swirl number in steps, so you basically go in these vertical paths, you find that there are path 2, path 3, and all the paths in this region 2 basically passes through some transition zones. Okay, and this is the entire basically stability map. Okay. So to understand the secondary transitions, we will come to this a little later. So let's look at the primary transitions over here. So as you increase the swirl number like this, okay, what you get is that first you get, so this is basically the chemiluminescence imaging superposed on basically the streamlines of the flow. Okay, so what you see is that you get a straight jet flame initially when the swirl number is basically equal to 0. And then you get the flame which stabilizes just as this is a wake type of an IRZ. So this just pushes the flame. So the flame actually stabilizes slightly away from the burner lip. But as you go on increasing the swirl number, where you actually go to the prominent vortex breakdown bubble, the flame anchors around it. And as you increase the swirl more, the flame actually spreads. So it is like it opens up. So you get this kind of a flame which is stabilized around the vortex breakdown bubble. So this is the whole history of the primary transitions that you get. So let's just look. So this map we have already looked at. In the case of secondary transitions, okay, here of course what you see is that an interesting thing that happens as you move now to the, so secondary transition always means that the Rossby number is very weak. So as you move on to swirl number of very high value, this is very close to blow off. Okay, what you find is that because there is a central stream always, okay, you get a conical tailpiece of the flame. So a part of it is anchored here and a part of it is basically stretched in this particular direction. As you go on increasing the swirl number, okay, this particular thing anchors because there is very strong straining effect that happens on the flame around here, and the flame becomes very short because of excessive straining as we go on to very high value of swirl number. And this corresponds roughly to the cases of the hydrodynamic studies that we did for non-reacting flow, except that now you have in the case of the secondary transitions for an isothermal flow, you had the secondary transition happening in that range. Here it happens over this particular range, mainly due to the heat release and similar stuff. Yeah. So roughly, to explain the possible physics behind the secondary transitions, once again, it's intuitive when you actually get a very high Rossby number. Once again, you can explain that there is a strong radial pressure gradient due to the rotational influence, okay? But that is low compared to the radial influence, and there is that the tailpiece basically arises because of the acceleration of the flow, okay, which actually stretches the flame in that particular direction. However, as you move on to Rossby number equal to 1 and even less than 1, the swirl basically stabilizes the flame, okay, and the flame tends to get very shorter because there is no entrainment effect anymore that is supposed to be seen. So I will wrap up in finally giving you the blow-off map, which basically is the normalized, we define something like an overall fuel air equivalence ratio. This is a non-premixed flame, but however there is a degree of mixing that happens because of the two streams interacting with each other. So if you look at, for example, if you look at this particular parameter, so you can see that this particular parameter actually decreases as you increase the geometric swirl number. And if you look at the corresponding variation in the strain rate parameter as well, so this is called the strain rate diffusion parameter. So it's very similar to the angular momentum diffusion point. Here also you see that as you move on to the high degree of swirl number, this strain rate diffusion parameter increases by quite a bit. It's almost like double. It just doubles itself. And I am not going to cover. So these are some of the high-speed chemiluminescence imaging of the flame, which basically shows the conical tailpiece. And as you move to close to blowout with very high level of swirl, the flame becomes stabilized and it becomes very, very small. At the same time, you do get to see prominent around say 12 to 15 hertz or 8 to 12 hertz frequency in the power spectral density of the OH chemiluminescence signal, which signifies you can visibly see the flame actually dancing like that. Okay, so these would be the conclusions that we developed. Basically, that how the VV modes actually determine the global flow structure as well as the flame structure, and what are the secondary and the primary transitions that happens. Importance of Rossby number and the acoustic response of such modes, and how the dynamics of the flame basically depends on the vortex breakdown mode around which it is stabilized. So it gives that hydrodynamic point of view to the whole problem. We have recently done high-speed imaging of the whole flow field, and we have been able to show that how these modes actually interact with each other also. So that data is not presented here. That's still being formulated as we speak. So this is basically the work. Thank you.
That's a nice presentation.
Thank you.
And we have a question or a comment.
Yeah.
Sometime back, we had done some simulations. The swirling gas, the transition rate, not terminal. And when you increase the swirl number, the frequency also changes. That Kelvin Hertz and other frequencies change. So you must have observed that.
Yeah, we observe, so that comes from the high-speed PIV data also. So that is still, I could not present it here because we are still deciphering the POD modes based on that. So there you could literally see that how, for example, in the VB, you have a very strong influence of this central piece. That means there is a lot of energy that is carried by those modes. Convectively, the vortex breakdown bubble carries a lot of energy. But however, as you move on to the higher swirl numbers, surprisingly, you see the convective layers becoming more and more energized, essentially. So, and the frequency also changes, you are right. But the change is, we have to document it a little bit more because there is a lot of cross interaction between the vortex breakdown bubble and this. So you get a lot of coupling effects. That means you not only get a single tone, you get a lot of sidebands as well. So
when you go to the flame, does the Kelvin modes disappear?
Well, it's supposed to be that case, but we do get that frequency. But however, that could be a resultant of this coupling mechanism. So it is very hard to isolate because ISL, OSL, and the vortex breakdown bubble which very strongly talk to each other based on different transport mechanisms. So yeah, we are trying to decipher some more of this puzzle. Okay, as we move on. Yeah. Co-flow temperature? No, in the isothermal, this is all isothermal, room temperature. In the other one is basically it's room temperature. So you ignite it and then, so it is that kind of. So it's partially premixed, I would say. No, it is still not, but because you have such strong swirl influence, okay, it's hard to believe that it is a complete diffusion flame also. So there is a partial premixing. So probably LIF kind of studies will reveal some of the. Yes. So there would be a lot of physics coming from that. So we will look into all these things, okay, with a little bit more details. Okay.
Any other question?
Yes, please.
What is reason for the Rossby number? What is the difference the Rossby number and swirl number?
How to measure them?
Yeah.
So we use a horizontal plane PIV. You can also do it through anemometry, and you can measure the U theta component. So that basically gives you the swirl number effect. Okay, and Rossby number is basically, this is the toppling kind of a moment. So because the two streams are moving at two different velocities. So Rossby number equal to 0 essentially means two things. Either both the streams are moving at the same velocity, so there is no velocity deficit along the interface. The other thing will be that the traditional flames that Jackie O'Connor and other people have studied, where it is like a bluff body, and you have the swirl coming around the bluff body. So therefore you have a basically wake stripe region, and then you have the vortex breakdown bubble sitting on the top of it. So this has also got that relevance because we wanted to inject the next part of the study that is going on. We are injecting basically liquid fuel into this. We wanted to check that if we introduce droplet clusters into a vortex breakdown bubble, what happens to the vortex break? It's basically to unearth the coupling mechanism between the two, because it's an absolutely unstable structure. So absolutely unstable structure is prone to it's supposed to be very unstable. It's supposed to be a metastable structure. So what is the influence of a liquid fuel? So that's why you had that provision. So, but this is all gaseous. So, but there is work that is going on currently in that category as well.